Hi, this is Calvin Cox. I want to do a real quick idea, throw it out there. This is part 3, and this has to do with how would you, once you calculate your numbers of how much calcium oxide per gallon is necessary to change seawater from a pH of 8.1 back to a pH of 8.24, then how are you, once you know that number, how are you going to do it? How are you going to apply it, okay, to the ocean? All right, and I'm going to draw this out as quick as I possibly can, get right to the point, all right? Okay, you have the ocean surface right here, all right, and you have a boat. Let me just draw a quick little boat right here, and if the anchor is over here, okay, and this boat is parked, I'm sorry, I hope we didn't get out of the picture. This is the ocean surface, and this is a boat. It's anchored. Okay, the current is flowing this way. The critical part is not the application. The critical, well, there's an application apparatus. I'm going to draw it in a minute of what I visualize. How would you do that? But the critical part, once you have the apparatus, which actually in a way is fairly simple, you have to do the calculation of how fast the current is moving past the boat. Okay? And I'll show you why right now. Okay. We're going to base this on hold on a minute, let me get a stick real quick so I can get this down better. I never script these talks. They probably should be, but by rights, a lot of times it just interferes with some natural information flow. So hell with that. Hold on a minute. Let me get one off. Okay, I'm going to use this handy dandy broom handle to help me draw some straight lines. Okay, now I'm going to go every 3 inches. You'll see in a second why this is important, so hang in there. Okay, this grid basically is a steel frame. It would be a measurement of I'm saying would would be a grid, a measurement of 70 feet wide by 14 feet deep. Okay, and you would have these little blocks. One of these little blocks equals this. Okay, one of these. 1 square foot is one of these little blocks. I'm not going to take all day to draw it precisely. It makes no sense. I'm just getting the point across. Okay, this would probably be made out of a metal tubing that was shaped like a little fairing. Okay, extruded steel, a good quality steel, or a good quality anodized aluminum. It would have to be anodized. And this basically would have each 3-inch little square would have at least one tube coming into the center of it. The tubes would probably run down through the center of that fairing material, would run down through the center, out a little hole that's been drilled, and come over and have a little hole where the mixture of seawater and calcium oxide had been mixed in a very specialized, precise metering system that all had a standard calculation based on the speed of this current that's flowing past this parked or anchored sea boat. Okay, basically this structure would come out. It would be a large arm that would hold the structure, and the structure would sit right at the water's surface and go down 14 feet deep, like this. Okay, the grid marks being like that would be these, and then it would precisely meter out in liquid form a mixture of seawater and calcium oxide. Okay, all based on how fast the current might be moving. Okay, if that current is moving at this speed, just what I did right there, that's like 3 feet a second. Some ocean currents, I do believe, move at that speed. Some move slower, and I think some move faster. Okay, so this system would have to be used in an area where there is an ocean current. Let the ocean current do the work and spread it around. All you're doing is applying a very specific amount through these little pieces of bent tubing to have a hole in the end, okay, and that precisely meter out a precise amount of mixture of calcium oxide and seawater that's in liquid form, okay? And the reason you have to do this is, I'm not going to draw all these, you get the idea. The reason you have to precisely meter it is because if you take a marine organism that has been living and breeding and reproducing in an environment that's a certain pH level, and you radically change that pH level, you'll literally kill the marine organism, okay? They can't breathe. That's like taking a human being and making them swim through a vat underwater of, let's say, apple cider vinegar and make them swim a mile. They'll die. All that crap will absorb into your skin and it'll kill you. You know, you can't, there are certain things you can't do. And we're finding out ocean life is so vast and so intense and so everywhere that even in the middle of the ocean, they say 1 liter has over 1 million different life organisms in it. And you can't go messing with that structure. As human beings, we already know that we're completely poisoning ourselves and our planet. We're upping rates of cancer and all kinds of other stuff just because of all the chemicals and everything we're putting out there. carbon dioxide, all the things we burn, create CO2, which is causing the oceans to acidify. And so now it's necessary to take action to change the pH level to begin to deacidify the oceans. And so the method for doing that is this right here. So you have to, let's say for instance that the current speed equals, let's go 2 feet per second. Feet. No, actually, let's do this. Let's take it down to 1 foot per second. Okay? Now, the reason that's important in 1 foot, in 1 second, every quarter second, okay, you're going to have 1, 3, 6, 9, 12. Every quarter second, you're going to have 1 quarter second equals 4 3-inch blocks. Okay? And so you'll calculate, based on that current speed, those every quarter second, you'll need to distribute or, let flow out from these little nozzles enough liquid to what it would change that seawater back. Okay? Now, remember, that's dispersed over 14 feet. So actually, we're going to change this from being what the top 1 foot was figured, I was saying, we're going to change that number and divide it by 14. Okay? And so you're not in reality going to be changing all of it back as much. You're not going to change it from 8.1 to 8.24. You're going to change it, take that number, whatever it would be, and divide it by 14. Okay, now let's do this. 8.24 minus 8.1, okay, is 14 and 0.14 equals 30% change. Okay, what I'm looking at, they're saying that scientists say that from roughly 1750, at the beginning of the Industrial Revolution, which is 265 years ago, mankind has changed the ocean seawater from basically what it was, 8.24, back to 8.1. In other words, it's making it more acid. Okay, so what I did was, I subtracted 8.1 from 8.24 and came up with 0.14. Now, the scientists say that when you go from 8.24 to 8.1, you're making the oceans 30% more acid. Okay? Because it's supposed to be on what's called a logarithmic scale. I don't completely understand it. I don't need to. But I'm saying that if 30% change, okay, and I look at percent, generally speaking, as being 1% is 1 part. So 30% would be 30 parts. So with my little handy dandy calculator, I'm going to say that if you take 30 and you divide by divide by 0.14 would equal, okay, let's try that again, 30 divide by 0.14 divide by 1/4. Divide by 1/4 2.14 equals 2.14. So that would be every foot that you go down, you would be changing the pH back, not the full 30% back, but every foot would simply be not 30 parts, but 2.14 parts. Okay, so it would be 2.14%. If I'm doing my numbers right. Okay, so you're not going to go back and say, okay, we're going to change this whole amount. Maybe you could.